We're going to do one more classic, I'll call it classic boundary value problem, partial differential equation, boundary value problem, called the Laplace equation. You can think of it intuitively as the heated plate. In this case, it's not a function of time, it's a function of location on the plate. What is the temperature of the plate at each point on the plate? So you'll have an X dimension and a Y dimension. And every point on the plate has a temperature. So our function U is a temperature. Here is the governing partial differential equation. Here, by the way, is another way to write it. It's just in case to introduce you to this notation, which I don't hold my students responsible for. What that means is this, which is the divergence of the gradient of the function, and that's 0. When you carry out this operation, it means that. So that's the partial differential equation itself. Now let's go through some boundary conditions. And we have 4 sides of this guy. For the first time through this, let's see, for each end of X. So along this left side, here we have X horizontal, Y vertical. Along this left side and along this right side, the plate is insulated. That means the derivative of the temperature is 0. There's no change in the temperature at those sides. Let's see, on the bottom, when Y equals 0, down along the bottom, the temperature is held at 0, or it is 0. These are the derivatives with respect to X. So there's no change in temperature in the X direction anyway. So that derivative is 0, that derivative is 0, this temperature itself, the function itself is 0. And then along the top, where Y equals B, it's just going to be some given function of X. So let's solve that problem. And by the way, you can have problems with all different kinds of mixing and matching of those boundary conditions. We've got 4 to play with. So let's solve it by product method. Let's look at this. This with the product method will be X double prime Y plus X Y double prime. That all equals 0. X double prime Y plus X Y double prime. Separate those, get all X stuff on the one side, all Y stuff on the other. And in this case, I'm going to set it to minus lambda. That gives us the convenient form for the X equation, which is kind of nice because those boundary conditions on those derivatives lead to the derivative of X where little x equals 0 and where little x equals a, those are 0. So this equation and these 2 boundary conditions allow us to solve completely for this eigenvalue problem for the x variable, the x function. If I had different boundary conditions, I might have used a plus lambda here to get it into the y equation. So it kind of, you got to kind of look ahead and see what boundary conditions you can solve the entire ordinary differential equation for, and you can do a full eigenvalue problem for. And we have a third one condition in this case, that when y equals 0, temperature is 0, which means y at y equals 0 is 0. So that's not a complete, that's only one of 2 boundary conditions on the y equation. That's not enough to solve the y equation. So we'll solve the x equation. That is an eigenvalue problem. You have the two derivatives. And this goes back to the case B I covered way back when at the beginning of this module. Remember I said, here's a common differential equation. Here's one set of boundary conditions, and that matches the one we're solving now. And as you go through that eigenvalue problem, zero is an eigenvalue. Here's its corresponding eigenfunction. Get all these other eigenvalues and their corresponding eigenfunctions. So let's go back to our problem. We want to solve that differential equation. Where am I? That was case B. So here are eigenvalues and eigenfunctions, which I just showed you where they came from. I didn't redo that eigenvalue problem again. We don't want to do it every time it crops up. It's going to crop up a lot. And once we have that, we have to use the same eigenvalue for y. So when let's look at the y equation. When lambda equals 0, which is one of the eigenvalues, just get y double prime equals 0, which means y equals like a plus bx, or y rather. And y at 0 just as a, that had to equal 0 because of that boundary condition, right? Because where is this boundary condition? This forced y equals 0. Ey as the eigen as the function, and we'll just set b to 1. So there's the eigenfunction corresponding to, or the y function corresponding to lambda equals 0. For all the other ones, there's a typo there. That should be n. Lambda sub n equals that from the x equation, which, and now we can solve this. So lambda is a positive value so for this equation, we have a negative value here that gives us the Cosine solution, general solution for y. But let's see, what is y at y equals 0? What is big Y at little y equals 0? That's 1, that's 0, so it's just a. That equals 0. So our function, y function corresponding to these eigenvalues, hinge. So for lambda equals 0, the total function is y, because u is just 1. For all the other ones, it's here's the x solution, here's the y solution, multiply together. Sum them all up to the general solution. So I get this up front and this infinite sum. This corresponds to the lambda equals 0, the eigenvalue of 0. These are all the other eigenvalues. Still have one more condition left. So this general solution here, what does it solve? It solves the partial differential equation itself. It solves these two boundary conditions, which means insulation on these sides, and it solves this boundary condition, meaning temperature is 0 along the bottom. We solve for everything except this condition. Yeah, temperature along the top. So our general solution equals that f of x, that temperature along the top. Well, this is not the general solution. This is the solution up at b, where y equals b. This was the general solution. So at y equals b, I put a b here and a b there. That's what the solution is at the top. That has to equal that f of x. So we're going to expand it using the cosine series. It's the first time I think you've seen that. The other ones we expanded with the sine series. Now we're expanding it with a cosine series. And if you go back to Fourier series, cosine series, this is what its form is. And we had formulas for this little a sub 0 and this little a sub n. We match coefficients again. We want this big a sub 0 times b to equal this little a sub 0 over 2. So we had a formula for the little a sub 0. It was this. And we want these a sub n's times the sin stuff, well, these little a sub n's of the Fourier cosine series. Here's the formula for the Fourier cosine series. We're matching coefficient. Big A sub 0 b equals this guy, and we have the a sub 0. So here's our solution for the big A sub 0. Big A sub n sin stuff equals the little a sub n. Plug in what the little a sub n is, and we have a formula for big A sub n. This. So here's our general solution. It's what we already had, but now we have formulas for the big A's. There's one example of the heated plate of the Laplace equation solved for one particular set of boundary